Hello and welcome back to the Oxford Online Maths Club. My name's James and I'm joined again by Ayliean.
Hello, so glad to be here.
It's good to have you back. Welcome back to the show. I'm also joined, of course, by people watching live wherever they are, but possibly wherever they are is Slido. Slido is a place where you can anonymously, or if you like, you can put a name in. You can join in underneath. It's where we run polls like the "How's your day?" poll. Ayliean, how's your day?
I'm getting quite close to a five. Somewhere in the region between four and five, I would say. It's been a very good day for me. How about yourself?
Ooh, I think I'm at four. I had a meeting. I had a meeting with some students. They've got exams coming up. They're stressed about exams. That makes me stressed about exams. I try and take their stress, of course, and make them less stressed.
Yeah.
But I think I'm at four. I'm willing to be at five by the end of the day, but finish strong. But yeah, okay. Chat at the moment is at 4.3, but it's one of those
Oh,
bimodal things where a couple of people have voted in there. If you'd like to join in with Slido, that is at slido.com/OOMC, which is where Hector and Milky Bar have said hello. I'll say hi to them as well. Oh, my computer is not incredibly happy. It's been happier as the votes come in. My computer has a three-star experience. If I'm losing frames, then sorry, I will try and fix that while we're going. Oh my goodness! Right. So last time we had Ayliean on to talk about Morse code. I don't know if people remember Morse code. So if anyone's got any follow-up questions about Morse code, Ayliean's back. You could ask them in. The Slido. Before we went live, we were thinking about my stupid one symbol version of Morse code, which
yeah,
was
yeah. I don't know. It's very clever. It's fun but impractical, I would say. I like it.
if you want to find details of my stupid version of Morse code, that's in the further reading notes from the previous episode. So if you get to the Maths Club homepage, which is on screen, that's not super helpful for you. It's in the YouTube description, and it should also come up if you put Oxford Online Maths Club into your favourite search engine. That gives you a page with all the previous episodes, including the Morse code one, which has a link to the YouTube episode if you wanted to watch that. Don't watch it now. Don't watch it two at once. And also a link to further reading, which is a kind of blog post of me putting some extra things in. Right, cool. YouTube is actually now quite unhappy with me, so I'm going to try switching some things on and off. And I think I'm going to hand over to Milky Bar joins chat and just says toot. So that's.
Oh, excellent. The best.
How's it going? Toot. Right. Yes. So we have a game, I think.
Mm-hmm. Yes, so we're going to start off things with a little game here. So James, this can be either me versus you or me versus you and the chat together. So you and the chat as a team, if you like. The aim of the game is to be the first to 15. So we're going to take it in turns to pick numbers from 1 to 9. Once they are used once, they are eliminated. They can't be used again. And the first person to have any three numbers which sum to 15 is going to be our winner here. So, James, would you like to go first or second?
I think we want to go first, and I am going to harness the power of chat. So I see we're going to choose a number, and it's like choosing people for your sports team or something. We pick, and then you pick.
Yeah.
And if at any point my team some three of the numbers add up to 15, then we're good. Okay. Right. Okay, chat. Here's how we're going to run this. I've got a poll. So if you're in Slido, you should get a poll to say which number we're going to go for. First vote has just come in for me to pick 9. I'm going to give the voting a second. We'll do a few. Is that A for? Yeah, there we go. Plus chat. There we go. At the moment, it looks like we're maybe going to go for the largest numbers because then we'll be really close to 15.
Okay.
We will see. What are we at with? Sort of a couple of votes for 9 at the moment. We're going to give that, although a vote has just come in for 1 as well. So I don't know. In between voting, if you'd like to explain why you voted for what you voted for, you can do that in the chat. I think in the Slido, if you're on your phone or something, there's like a selector at the top to switch between Q&A and the poll. If you want to. If your phone is currently just looking at the poll, then you can, I think, switch to chat if you like. Right, good. Yes, my computer hates the voting. Voting is currently going for 9, so I think we might go for 9. Yeah,
Okay.
I'm going to call that round of voting there for 9. We've picked 9. Your turn.
So James and chat pick 9. 9 is gone. I'm gonna keep it. I'm gonna keep it in the middle. I'm gonna go for 5.
Oh, right, okay, that was very speedy as well. I just need to. So I should not let chat pick 9 because we already picked it, and I should not let chat pick 5.
Mhm.
Did you say because it's in the middle? Ooh.
Yeah, I just you're going for high numbers. I'm gonna keep it steady in the middle.
Okay, so if we get any two numbers that add up to 6, then we're good. Right, okay, so chat, you know where this is going. Okay, so Milky Bar has a kind of plan that we're going to go for 1 plus 9 and then 10 plus 5. So at
So
the
I've already
moment,
got 5. So bear that in
you
mind.
have taken the 5 away from us, so I think we might. I kind of don't want to pick 1 because if I'm trying to win in just 3 moves, then
Mhm.
you've already blocked me there.
Mm.
Right, what's this coming in? This is. So there's a vote for a 4. I don't mind a vote for a 4. I sort of see. So if I pick 4, maybe I shouldn't do our game plan out loud, chat. I sort of have to talk to chat. But don't listen to this bit, Ayliean. Yeah. Okay, we're gonna pick 4, and then thinking about picking 2 after that, right? Because we've still got 6 to go. Right. Okay, and that looks like what we're gonna do. We're gonna try and do that. Let's hope that Ayliean didn't hear any of that. Right. Good. Okay, we're picking 4.
So you're picking 4.
You can't use the same number that they've used. Yeah.
Yeah. Do you know? I feel just of my own volition that I'm actually gonna pick. Yeah, I'm gonna pick 2.
The chat, that was the number we wanted.
Yes.
But it's not over because your numbers. What have you got? You're 5 and a 2.
Yeah. So now the tables have turned. Maybe you're gonna end up kind of blocking me, because
Okay.
I feel like I have a plan here.
I reference quite a lot. Quite a lot of things on this show remind me of Twitch Plays Pokemon. I probably referenced this last time you were on. I'm sorry, but Twitch Plays Pokemon was an experiment about 10-15 years ago to get all of the chat viewers together to control a character playing a Pokemon game. I get every time we do this kind of audience participation, we put something in the hands of chat. It's going great though.
I mean, I am a massive Pokemon fan. Do you have a favorite Pokemon?
Yeah, Arcanine, the one that's just a big tiger.
Yeah.
Chat has not yet realised how funny it would be to just force me to pick the wrong number. They are picking 8, which is good of them. So we're picking 8, which doesn't help our own cause because those 3 don't add up to 15.
No, but I need to think now. So what I was going for is definitely gone. But you have an 8 and a 4, which is going to give you 12. So, like my hand is a little bit forced here at 3. Like I don't really have free choice so much anymore. I only have 3 choice.
Sorry.
So yep, I'm gonna have to go with the 3.
Okay, we're trying to make 15, I think.
Mm-hmm.
I've got a vote. Is it just 1, 6, 7? No, I need to remove 3. Hang on a second. I need to remove 3 from that poll. So just 1, 6, and 7. Is any 3 of our numbers making 15?
Any 3. Yep.
So 13 and 2 is not in there. 17 is already too much. 12, you've taken the 3. What are we going for? We're going to clever 2-move plan. Oh, you should also worry about what you're going to do because you've got 10 already. You can't have another 5.
And I wonder if chat has an opinion. So you chose to go first. Are you enjoying that decision, or is that something you could pick differently next time?
Hang on, let me set up a poll for "Are you enjoying this decision?" I now send all questions to chat. It's not unanimous, but chat thinks we should go for 7 next.
Okay.
We did a whole graph theory thing like this once, just moving around the graph, but choosing which way to go. I'll think it in the further reading. Oh, I suppose it's just more audience participation. We've picked 7, I think.
Yeah, which like absolutely would have been the number that I was going to pick next.
Oh, well done, chat.
Yeah. So.
Because 5 and 3, right?
Yeah, I think at this point, I don't think we're gonna get any winners. You can surprise me, but I'm gonna pick 6.
Okay.
Yeah.
And then I guess that takes up 6.
Yep.
And then we have
What's your chat gonna vote for now?
Slido actually won't let me run a poll with 1 option, so we're gonna pick 1.
1. Okay, cool. You're speaking for the whole group here. You're
And
gonna
then
pick one.
I've got 5 choose 3 things to check, but I don't think we've made 15.
Hmm.
No.
So I mean, that's another good question. Is like, how many ways are there to make 15? Would be a fun
That's a
thing
good
to look
question.
at. Yeah, 3. So then you went for 7, I went for 6, and we finished up on 1. Now, was chat happy with their decision going first? Does it feel like a difference if you had gone second and I had gone first?
I sort of feel like, I don't know, so chat hasn't given me an opinion yet. I will keep an eye out for chat's opinion and I will think out loud, which is maybe helpful, maybe not. So this feels to me like the sort of thing where you want to go first. I don't know. If there were just some best numbers, if going first was good and I could pick some numbers.
Mm-hmm.
Wait, no, hang on. Yeah, proof by contradiction. If going second you could win, then going first you could just do something like, well, you can't really pass the turn, I suppose, but you could pick a terrible number that you weren't planning to use.
So we ended up in a back and forth there where I could block first because you chose to go first. So I had a little bit of an advantage and I could see what you were going for. You were the first person to pick 2 numbers, so then I blocked. But then you were continually blocking me, and I was continually blocking you, and we ended up in a draw. And I wonder if that kind of game structure, that feel of a game where you're blocking, and then it always ends in a draw, if that's a familiar game to someone. Have you ever experienced that during playing a game?
Yeah, like chess, right? And loads of them you take it in turns. So chat now thinks we should have gone for 5. There's a tiny bit of infighting, I think, that chat thinks we should have gone first, and we should have gone for 5 to start with. I think they saw you pick 5, and
Uh-huh.
I think some of them had voted for 5.
Okay.
And opinion in chat is this feels like probably it's going to be a tie if both people play perfectly. Possibly
Yes.
if Hector thinks that the second person can block more, but I guess blocking on its own doesn't make you win. Blocking makes you not lose,
Yeah.
which is
Absolutely. Your chat is very observant and entirely correct. If both players play perfectly, unless someone makes a mistake, nobody will win. It will always end up in a draw unless someone makes a mistake. Um, and there is a reason that I picked 5 first. So it's a fun thing to like enumerate yourself, but there are eight ways in which you can use 3 numbers to add up to 15.
oh
So
yes, I forgot to.
yeah, you can make a fun list of them yourself.
I forgot to think about that. Oh yeah, okay. That's going in the further readings. Further reading notes. 8 ways to make. Oh, okay, 8 ways to make
8 ways
15.
to choose 3 numbers from 1 to 9 that adds to 3 distinct numbers from 1 to 9 that add to 15. Now the reason that I chose 5 is that there are 4 of them. 4 of those ways include the number 5. So 5 kind of comes up in the most in all of those sums. Is this your? Are you visualizing a
I'm
seesaw?
thinking about where the 4 are. Right, you've got 4. Yeah, you got 5 in the middle, and then you still got to make 10. Ooh, number bonds. You got 4 things on the left, 4 things on the right. That'll be alright, won't they? Yeah, okay. 4 ways to make 4 ways using the 5 in the middle, and then.
Uh-huh. But I think at this point your chat is probably they're being very patient, but we
Oh,
came to talk about magic squares. So let's have a look at a magic square. And before we even talk about how squares become magic, I want to have a little replay of our game. So this is our actual game. If the numbers, instead of being arranged in a line, were arranged on this square here. So you started with 9. You took 9 straight away. Now, I think maybe you can see why I went for 5. So there's me on 5. You went for 4, in which case I was entirely forced to take 2. Numerically, the chat then noticed that you would have to take 8. And you can see that as this plays out, it becomes entirely synonymous with a game of noughts and crosses. I took 3, you took 7. At this point, neither of us were winning, but I took 6, and then you took 1. And here you can see all of the 8 possible ways, all of the 8 things which we were going for. So 9, 5, and 1 gives us 15. 2, 7, 6. The sum of those would give us 15. 3, 4 and 8, 15. And we can see all of the rows, all of the columns. You can just double check, make sure that I'm actually, I mean, it's getting late at night. My arithmetic goes towards the evening. But the columns also add to 15. And importantly, as a tactic in noughts and crosses, the diagonals also give us 15. And now we have seen our very first magic square of the day. Woo!
And shout out to Joe and Sherry and Milky Bar, who at some point said noughts and crosses. There was an anonymous person who said noughts and crosses really quite early that I didn't read out. But well done to people in chat who spotted that. I think did we get tricked into playing noughts and crosses? I feel a bit tricked into playing noughts and crosses. A game that I might not have agreed to play.
Yeah, so this
At least we didn't lose.
secret surprise noughts and crosses, which we did well. So there are 8 possible ways of making 15, and so we can arrange this into a magic square because we have those 4 overlapping sums, which include 5. So let me just erase my pen here. What do I want? Yes. So here's a magic square, and I think this is this the first time that you have explored magic squares on the Oxford Online Maths Club?
Yeah, that's right. Even if you've watched all 100 episodes over the course of about 5 years, we've never done magic squares. So
I honestly, yeah, I have to say that I am honoured to bring magic squares to the OOMC, because they're an obsession of mine. They're beautiful. It's such an amazing piece of recreational maths. So just to make sure we cover the absolute basics before we dive in, we have such a rabbit hole to go down. What makes this square magic is not that you can play noughts and crosses on it. It's that all of the rows, all of the columns, and all of the diagonals add to the same thing. So that's our definition of a magic square. We're adding up like 2, 7, and 6 gets us 15. Rows, columns, diagonals all add to 15 in whichever way you look at it. And there are different types of magic square. So this one, confusingly, is called a normal magic square because it contains all of the numbers 1 through to 9 exactly once. I don't know why the terminology normal came around for that, because there are more magic squares which do not have this property. So it is an unusual magic square in this respect. James, do you have a favourite magic square?
Oh, this will sound really rude, but aren't they all the same? Aren't they all the same, right? They've got the 5, because I think all the ones I've seen have got the 5 in the middle, and I think you can, and then the stuff around the outside, but isn't there only one magic? Maybe that's a nicer way of saying it. There's only one magic square, right? Or maybe not. I'm not sure. Until you show me a second one, I think this is my favourite one. Until you show me a second one.
Cool. So it's definitely a good point that there are some operations you can perform here that would retain the magicness. Like you could rotate it 90 degrees and it would still be a magic square, but it would just have 4, 9, and 2 up top. Or you can swap. You can swap the top and the bottom row, things like that. So what you're saying, the ones that you've seen, they all have 5 in the middle, and that is a good point. But they don't even have to just be 3 by 3. Like you can get them in loads of different shapes and sizes. So this is an old school famous etching by an artist / mathematician called Dürer. The etching is called Melancholia. I think the angel here is supposed to be very melancholic. Interesting shape going on at the side. There's a lot of debate as to what this shape is and what it represents. But I am most interested in what's going on in that top right corner. So enhance. Here we have a 4 by 4, and it is a magic square. You can check the rows, the columns, the diagonals, they all add up to the same thing. I will actually, because
there's a couple that are hard to read.
Yep, there's a little bit of artistic liberty taken with particularly these 2 numbers here. They are supposed to represent a 5 and a 9. So here's a more readable version. This painting, etching, was made in 1514, so that's quite cool. You got the date in there. But I wonder if chat can see, not only do the rows, columns, and diagonals all add up to the same thing. Well, first of all, let's get the magic number. What are we working with here? Okay. So 16, 3, 2, 13.
Right, so you're telling me that all the rows and the columns add to the same thing, So actually, I could choose which row I wanted to add up if I thought that one of them looked easier to add. Oh, I'm actually going to add the bottom row together because it's only
Okay.
got two large numbers in it.
Mm.
Yeah, okay. So 29, and then I can see a 1 and a 4. Chat joining in as well. Chat says 34.
34, and you can check them. But I wonder if chat can find any other combinations of numbers on this grid which add to 34. Let's have like a little free for all. So it doesn't just need to be the rows, columns, diagonals. There's quite a few 34s hidden in here. So we're looking for four numbers which add to 34 in here.
Right. Okay. So is there some sort of like linear algebra thing here? Like once you've got some things that add to 34, you can do, I don't know, twice the first row minus the second row. Maybe that's not what you mean. It's like
we're only dealing with plus here. So I want you to try to pick four of these numbers which also add to 34.
Oh, right,
so
okay. Here comes some chat suggestions. Chat's got several ideas immediately, all at once. Middle four squares. The inner
middle four, yes, middle four works.
The corners, I think. Ruben says. Oh wait, no, that's not quite what Ruben said. What was Ruben saying? The outer four two by two squares.
I know exactly what they mean. So if you were to split it into four quadrants, each quadrant also adds up to 34. Yep.
I'm picking the one with the large numbers in 26, 28. Oh my goodness, yeah, okay. The middle, wait, what? The middle of each side with the opposite side. 3 plus 2 plus 15 plus 14.
Yes. So yeah, exactly that, and also the left and right.
That's like the corners. That okay, but that is kind of, that's two rows minus the corners. So that's what I mean about the linear algebra sort of thing, right? The shape becomes like two rows like minus. Okay, maybe I shouldn't double a row, but.
So yeah, and then here's the middle square that we were talking about. We've managed to find the corners, and we can also get one away from the corners, and that works in both directions as well. So this is really awesome, this 4x4 magic square. So at this point I'm hoping you think they're not all the same,
No.
but maybe you're thinking, okay, well this one's only extra cool because it's a 4x4 and the 3x3 ones all have to be the same. So let's have a look at these magic squares here and just convince ourselves that they are definitely magic. So they do have different totals, that's worth pointing out. But, just do a quick run through.
Someone said that the total can be anything in chat at one point, and I think maybe they were thinking about this, where you can have squares that are magic. So on the left, those things maybe add up to 45. It's not obvious to me how you've done that as well. It's not like you oh, maybe this is something that I thought of you could do. So the previous one added to 15. This one, I think all the rows on the left there add up to 45. So mischievously, I thought, I wonder if you've just multiplied everything by 3, but
which you can do. You can scale magic squares up. Yeah, so you can multiply them by a single number as long as you times everything by that same number.
Yeah, that's the linearity of magic. So on the right you've got.
Oh my gosh, I have to write that down as a quote for future. The linearity.
But that's not what you've done, because these numbers on the left are not all multiples of 3. There's no common factor.
Oh yeah, it's a different magic square, fully. And on the right, what have we got for our total here?
Well, I mean, it looks like 21. I'm not going to make chat do the adding. It looks like 21, and I've thought of something else. Can you do? Okay, no, this time there's no small numbers here. I think this one is related to the one that I've already seen. And now I'm suspicious about the left one as well. Chat, can you work out what's going on here? I don't know why I'm taking the anti-side and trying to show the magic squares.
I think I can maybe see a link between the one on the right hand side and the first one that we looked at, but the one on the left I don't think is really related to the one that we were looking at. I'm just going with like odds and evens. So in the numbers 1 to 9 you have 5 odds and 4 evens, and so the evens end up being arranged in the corners, whereas on the left hand side it has an entirely different arrangement of odds and evens. So they are like different magic squares. But however, taking like a fresh sheet, These two magic squares are linked, and I have been nothing but impressed with the chat at the Oxford Online Maths Club. It's a really tough link between these two magic squares, and I don't know. I was going to say eat my hat, but actually I have too much faith in your chat. I will be incredibly impressed if you can find the link between these two magic squares.
Right, Joe thinks that the one on the right is two more than the original 3x3 magic square you showed us.
Yes, so again, because of the linearity of magic, you can add the same number to each of them. Actually, you can add two magic squares together, like, square by square, and it will also result in another magic square. It's a fun one.
Oh, that's good.
Yeah,
Linearity of magic.
it's
Right, okay.
But you can't multiply them together, which is frustrating. It's like matrices.
Okay, so Joe's convinced me that the one on the right is very closely related to the original. So if you're telling me these two are secretly related to each other,
no, the link is not. It's not a linear or mathematical one. I'm gonna change it to written down in English to kind of give you, because this just blew my mind when it saw. It's just like a fun fact, but here is a legit magic square. It's written in English. So now, considering word wise, so we're looking like at the actual words for the numbers. What's the link?
Oh no. Oh no. Oh
What?
no. Well, I saw someone in chat just says ha 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 instead of typing out what's going on. Ruben's thinking about matrices and eigenvalues, which I do want to come back to, but
Can we talk about matrices and eigenvalues?
not sure. I think I might put something in the further reading notes.
Yeah.
I think it's the sort of thing where some people have seen matrices and eigenvalues, and some people have entered the matrix, and some people would like to find out more via the further reading notes rather than here. Joe says the number of letters is the same.
Yes.
In each row.
So this is just emblematic of some of the unbelievable feats that human minds have achieved in terms of the constructive constraint of magic squares. So you can see 2 is a bit easier. TWO, that has 3 letters, and over here we have a 3. 25, if you want to count it out, does have 10 letters. 18 EIGHTEEN has 8 letters. Now this is not a property of all magic squares. This is just a very, very cool, interesting one where the left-hand magic square, if you count the numbers, count the letters in each number in English, it will generate another magic square. It's beautiful.
Oh, thank goodness. When I saw it, I thought with horror that you were going to tell me that they were actually anagrams of each other between the rows. They were not quite, I realised eventually. But yeah, okay, number of letters, still very cool.
Yes. Yeah. I mean, maybe that's something that you can invent. So we've seen 3 3x3 magic squares now, and you kind of almost there with figuring out something to do with the middle number. So maybe consider.
What did someone say? Someone told me something in chat. What did they say? Someone said something. It was an anonymous person said something like, "Is it something to do with 3 times the one in the middle or something?"
Yeah. Well, let's just check it out. So here we have. We knew that the magic total here was 15, and the middle number is 5. Here you worked out. I think we're using the first column, but you got a 45.
Yeah, which is 3 times as large, and the middle number is 3 times as large.
And then here we had a 7, and we end up with a magic total of 21.
Which is 3 times 7.
Yes. So there is a rule that in a 3x3 magic square, your magic total will always be 3 times that central number. Now, I think your chat will be okay with this, but reel me back in. I think that we can prove that that's always going to be the case for all magic squares. It will involve a little bit. Yes, it'll involve a little bit of algebra. So I think consider how would you go around proving this? The numbers can all be different. It's a little bit daunting to start with, but yeah, we're gonna give each of them a number. Now, a letter. I deliberated whether or not I was going to make it I or skip to J, because obviously I gets it overused and it looks like a 1. And some people, I'm sure, are already looking at complex numbers, but I went with the I anyway. Okay, so here we have a magic square, but we don't know it's magic yet. It's just a grid of numbers. So we're going to define, we're going to say it definitely is a magic square, and the magic total is m. So we know all of the rows, all of the columns, all of the diagonals, they add up to m, this magic total. Now, it is worth remembering that when you are trying to prove something mathematically, you have to pretend you don't know it. So we do not know that if you do 3 times the middle square, you're going to get the magic number. Yeah. But you kind of want to keep it in the back of your head that ultimately we want to figure out that 3e is equal to m. It would be nice if we could forget that and then show that it will happen for all of the cases. Cool. Okay, so at this point, I imagine your chat is very astute. Have they already started giving us some equations that we can create here?
There's a joke about complex numbers, and there's a suggestion about what we're aiming for. We're aiming for this. Chat is going to tell me it's going to be a little bit hard. I think chat don't describe the Okay, so chat says they've got 8 equations with 9 unknowns. Yes. So the aim is to try and make everything in terms of E.
Oh, okay. So we're
ambitious, I think.
It is ambitious, very much ambitious. But it is a good thing to kind of look at how many equations do you have, how many unknowns do you have, because if you have more unknowns than equations, then you're probably going to run into a bit of trouble unless there's a couple workarounds. I'm gonna lead a little bit because I'm certain that you could get there with enough time, but we know that this central E is the overlap of quite a few of those equations. So originally that was the one that I had as 5, and I picked it because it was the overlap of 4 different ways to get 15. So I'm gonna kind of quantify like a vertical and a horizontal together and take them together. So if I took both of these 2 equations together, that would give me something along the lines of B plus E plus H plus
one magic sum.
Yeah.
E plus, okay. So another magic sum the other way.
Yeah, is equal to, so yeah, you're right, I've got a magic sum one way and a magic sum the other way, so here my total is going to be 2 of those magic sums. Is my pen showing up? Would you like me to change it to black?
I think it's alright.
I'll change it to black.
Okay.
Yeah.
You've got that one and that one. Yeah, I'm trying to sort of plan ahead as well to say we want loads of things to cancel. Carry on though.
Okay, loads of things to cancel, but every so often because we're doing simultaneous equations essentially, there's a kind of trick that you can build up if you have enough overlap. So let's look at the diagonals now. So we'll create a similar kind of equation but for the diagonals. So we're going to have A plus E plus I plus C plus E plus G. E plus G. And once again, because this is 2 lots of magic sum, we're going to end up with 2m. Okay. And here, yes, you could try and do some cancelling, or I wonder if anyone in your chat has realised the little thing that we can do. James, have you noticed what we could do here?
Nope.
Wonderful.
I sort of think I have an idea about, I know what I would do next, but I don't know if it would work. And that's often the thing, that often means I should just go and try it quietly, right? That I'm maybe the thing that I'm willing to do is just try stuff and find out if it works. I never know if it's going to work or not.
Yeah.
Chat, I don't know what they would do next.
I will tell you, like, on my journey to this is a nice way. It is also this is what I got on my round 2. So I did this a very long way with the 8 different equations. And then once I'd been through it once, I was like, I think I can do this a nicer way. So sometimes round 2, you get a little bit more insight. So don't think that this is, I looked at this and did it like this the first time. This is how I did it the second time round. So if I were to take both of these equations and just add them together, adding both of these, let's see what I would actually have. I would have A, and convince yourself I've got A, B, C, D, Let's just double check that I've got all of those exactly once. A, B, C, D, E. But actually I have a few E's. I've got 1, 2, 3, 4. So I have 4 E's. E is going to be the weird one here. So I've got 4 E's. Then I'm back to my single F, G, H, I. Okay. So F and G and H and I. Okay. And this is going to be equal to 4M.
Yeah.
Nice.
Adding together even more things together. That includes all the letters around the outside.
Yeah,
I'm trying to work out how to cancel.
It looks like we have all of the letters all together and some extra E's. So is there a way that we could put all of the letters all together, and A, B, C, D, E, F, G, H, I, into terms of M?
Yeah, okay. We know the sum of everything. So Ruben in chat at the moment says the sum of everything is 3M. That's not obvious to me, but I suppose...
Yep, I can get you there. So A plus B plus C is M.
Right.
D plus E plus F is M. And G plus H plus I is M. So if you just look at the rows, here's an M, here's an M, here's an M. And that is all of the letters once. So we got 3 M's. Yeah?
Yeah.
If you want to see it in a kind of cancelling down way, we've got A, B, C gives us M, D, E, F gives us M, G, H, I also gives us an M. So we've got 3 M's and also 3 extra E's, because we only need to use one of these E's. So we have 3 M's and 3 E's is going to give us what we had before, 4M. And at this point, we just need to subtract 3M from both sides, and we get 3E is equal to M. What?
Nice.
Isn't that
what you wanted in your dreams?
Yeah, I've dreamed of this moment, and here it is. Yeah, it is nice. So it saves. This is what I think is the beauty of algebra, because we've done 5 lines of algebra here, and we've settled it. We do not need to look through. There are infinitely many 3x3 magic squares. We don't need to check through them all. We know for certain that the magic number will always be 3 times the central number.
Nice.
Yeah.
Like it. There's a. I'm trying to think. So there's a step in there where you had in your first line in pink. There's D plus E plus F, and then you subtracted that later on. So maybe this ruins the symmetry. Somebody says really satisfying or symmetric. Rosie says the sum of all gives 3M. Very nice. We get every term, but E is repeated every term is the key observation. My shortcut would maybe avoid that lovely symmetry, but I've realised it's weird that you had the DEF and then we subtracted it at the end. So possibly there's a way to go. Yeah, it's the diagonals and the vertical minus 2 of the rows, the top row and the bottom row. So you go AEI, BEH, CEG. And that gives you 3 times E, the thing you want, but also the top row and the bottom row. you subtract those off. So if you, but that breaks symmetry quite badly, because then I didn't mention D and F at all. But I probably wouldn't have spotted this. So I can, if that was your second way around, then maybe my third, if I count your 2 as well, my third would be like the right combination was that equation plus that equation plus that equation minus those 2 equations or something.
Yeah.
Maths is hard.
and cool, and there's also like so many different ways to get to the same answer, but what you end up doing is just convincing yourself more that we've definitely got this. It's good to see it from different angles. So yes, 3 is always going to be the middle one. Now, you've had some speculation that there is an underlying structure of magic squares and that they're maybe all related in some way, which is true, but they can be. There is an underlying structure, but there is also infinitely many, and there's infinitely much variation between them. So I wonder if we can give ourselves some constructive constraints and maybe start creating magic squares knowing what we know now. So let's see if we can make an all even number magic square just for fun. Obviously the middle number will need to be even, so what would that be?
Is there chat could choose an even number to put in the middle?
Any even number.
Oh, we're looking for any even number.
Yeah.
Okay, if you let them pick any even number, then they really will. I mean, Ruben says the sum has to be at least 12, but if you say any even number, then
This brings up a point that there are some magic squares that contain negative numbers, and that is a matter of taste, and
right.
some which contain decimals. Again, it's just up to you whether you like negatives or decimals, whether you want them in your magic square. So yes, if you pick one sufficiently small, then it will go into the negatives, which I don't mind, but
Mm.
um,
I,
yeah.
I now you got me thinking about like a complex number magic square, but I suppose that's just a real one and an imaginary one.
So have we got
So
at
there's
least
addition
something
is.
that's come up a few times? Are we going with
Oh yeah,
12?
sorry. The chat says 4 and 0 and 7 billion. So 65,536. I think they're trying to cause an integer overflow. Um, uh,
Okay, I'm
yes.
gonna I'm gonna have some selective hearing here. Well, let's just go with 4 then.
Okay.
Okay. So we now know that our magic total is going to be 12. Um so we know that it's always going to add up to 12 because we're going to get 3 times the middle. So then since we want it to be an all even magic square, it kind of creates this almost Sudoku feel. You get to pick 2 other numbers and then it becomes fully defined. So right now there's many that we could choose from. Let's just go with, say, I don't know what we have, a 6 here. Could pick any even number. We'll go with a 6 here. And now this one is forced because we know that this is going to have to add up to 12. So very similar to like when you're trying to win knots and crosses, you go like middle, and then if you pick here and here, you have 2 different ways of winning, and you win it. So now we would know that this would be 2, and then again you have free choice here. So James, have you got an even number that you'd like up
I
here?
see. I was reading Rosie in chat is talking about parity rules so that all the magic totals are even, but you want actually all of these numbers to be even.
Mm-hmm.
Can I go 0?
Okay, sure. Um, 0. So that means that we're going to have an
Oh,
8 here.
oh yeah, I've seen. Yeah.
Yeah, and then so we've now got a situation where we have 2 of the same in a magic square, which is contention. Again, this is a matter of taste. So we'd end up with a 2 here. We're going to have a negative. So a minus 2. Wait, am I right in that?
-2, I think. Yeah. Because
Yeah,
I've got 14 so far.
yeah, minus 2. So we need a 10 over here, and then it's just like a cool little Sudoku. We get a 4 up here. So it is entirely up to you whether you like this magic square or not, because it has 2 2s, it has 2 4s, it has a 0, it has a negative. But this is how you would build up a magic square, like containing some sort of property. They're all even. Will give
Mm.
us that brief
But
net, but so would a magic square that was all 2s. That would
yeah,
also be all even.
I think if you're allowed to
Um,
repeat numbers, then you can make them all the same.
yeah.
To quote a
So
famous number file video. Um, Ruben
I
says,
guess
there are not enough even partitions of 8, which has really amused me. I think this is the person who suggested we put 4 in the middle. Isn't
ah,
You've been forced to
I
use
guess
repeating digits.
something that your keen beans can think about in the further reading is how would you then generalize this if you had x in the middle and then you want there to be some sort of difference between this square and the other square, so you can have either x plus a or x minus a, and then go through and create like the algebraic form, because you really only need these 3. Once you define these 3, the rest of the magic square is fully defined. You've got no ways around it.
Right.
Yeah, there's a couple other configurations you could do. Basically, the configurations you're aiming for with knots and crosses will end up defining a magic square. So, um, I am conscious of time, and
Oh, yeah.
I don't think that you realize just how cool magic squares can get. And there's some magic squares that I really, really want to show you.
Okay, let's go. We've got maybe
So,
15 minutes.
this is an all-even magic square, which is a cool enough property. Yeah. But we can do cooler. So you could say, what about an all-odd magic square? Now, here's an all-odd magic square, but it's not just all-odd. So these numbers are massive, which ironically means that they have to be written very small. So sorry that the font is tiny, because the numbers are very large. So what's the smallest one here? And I imagine that chat's probably going to start noticing some similarities between these numbers. I think this one is the smallest one, which would be 1,480,028,129.
Something like that.
Um,
Yeah, I think that's the smallest one on screen. What on earth are these? You don't need to
What
use
are
numbers this
these?
large to make an odd perfect square.
Yeah, well, you could, because you can make, oh, for sure, you can make a much smaller odd magic square. So why did we pick these ones? They're not only odd, but what is a cool property that odd numbers sometimes have?
Oh
um,
no. Oh
oh no,
no.
has it clicked for you?
Yeah, I think I've guessed what you've done. I haven't checked what you've done, but I think I've guessed what you've done. Chat can guess this as well, I think.
Yeah. What are we thinking?
Uh, oh, did we? Apparently, the previous one with all evens we might have messed up, and it
Oh
didn't actually.
no,
The middle column didn't actually add up to 12. So no, that's homework. Don't worry. They're going to go in the further reading.
that'll be my negative. I'm sure I did that wrong. It was supposed
Oh,
to be negative.
Rosa says, are these all consecutive primes?
Oh my
This is
god!
secret.
What? Yes, they are prime. So they are prime, but not only that, they are 9 consecutive primes. So from this number here, 1,480,028,129, the next prime number after that is, I think, this one down here where it ends with the 141. And then there's no prime numbers in between them. And then when you look at the next prime number on, you get the 153, I suppose, and it keeps on going up like that. So this is a run of 9 consecutive prime numbers, which create a magic square.
I think does any arithmetic regression of length 9 in the primes probably works. I think if you lay them out in the pattern of the original one.
Okay, so this is a kind of interesting side question.
Oh.
Yeah, So do you know much about like arithmetic progressions of primes?
Well, I've heard of the green towel theorem, so there's loads of those. This is going in the further reading notes. I think if you can find 9 prime numbers with a constant difference like that. Oh, do they have a constant difference? Oh, maybe not.
Have a constant difference.
They don't. Do they have a constant difference or no?
I don't
Maybe not.
They do. No. Someone will correct me on this.
No, 29. They don't, do they? Because no. Okay, right. It's not an arithmetic progression. Cross that out. There's a small difference of 6 down there. No, this is actually weird. I keep wanting them. I keep wanting them to be simply related to the original one, and they keep not being related to the original.
They're not all the same. So like this is cool. This is really nice. And then like I say, magic squares come in all different sizes and shapes. So I'll give you the font on this one is quite horrible. Now we do have to make a small concession on this one. It is consecutive primes, but I think chat will immediately notice one small like fudge that has been made here with the consecutive primes, which is top left corner.
Yeah, just one small problem.
Yeah, just one. So the number 2 is not included in here, which is a prime, and instead it has the number 1. So it's the odd primes plus the number 1. And I think this is an 11 by 11, 8, 9, 10, maybe a 12 by 12, 3, 6, 9, no, 12 by 12. So it's a 12 by 12, and it is consecutive odd primes plus a bonus 1, arranged in a magic square. And just when you start looking at like all of the things that are available, it just becomes more and more ridiculous. So again, here is another all prime magic square, and I want you to think, okay, so here's one, and then I go poof, and it changes. What's the difference between these two magic squares? Not the as in subtraction difference, but like looking at them, what is the difference? Here's one, here's another. Goop.
Wait. Well, so there's some ones in the second one. Are we allowing one as a prime? No, wait, we're not.
So the second one is not all prime. The first one is all prime.
Okay.
Because this one's got 4 in it and everything. Yeah. So what is the transformation? What's happened from the first one here to the second one? And both of them are magic squares. I feel like a mathematical optician here. First one, second one.
I think you made the second one first.
What? Do you know
Oh,
what?
did
That
you
would have
not?
been really smart, James. I wish you were there when I did this because the smart thing to do would have been draw the second one and then, because what's happened is the units column has been removed, right? So you draw the second one and then you fill in the units column. But if you look really closely, I didn't think that far ahead. I drew this one first, and if you look very close, there are tiny little black pieces of square paper covering over the units column.
I didn't even... It's not even a Photoshop. It's a physical.
Yeah, cut
That's
out
so
things.
you. Sorry, it's a craft activity to. Oh my goodness! Yeah, okay.
Yeah. So this is really awesome. And do you know what? When you look at things like that, it's cool that it's prime. That is one of the difficulties. But you have already noticed how you would construct something like this because you can take this magic square, multiply everything by 10, and it still gives you another magic square. And then if you add whatever separate magic square to it, it retains its magicness. So that's how you can create these magic squares where you can remove the units column and it's still magic. Yeah, just move everything one order up and add on another magic square. So this is very nice. But then it gets to ones where I honestly have to wonder how on earth like human brains came up with it. So this one here.
Why has it got? Don't tell me no. Why has it got thick lines around? I'm very nervous now. Whenever you show me a square.
This is, once again, on the theme of all prime magic squares. And is this a 13 by 13? 1, 2, 3, 4, 5, 6, 7, 8, 9. 13. Okay, so it's a 13 by 13 magic square. But as you've noticed, there are some thick lines on there. And if we, on this 13 by 13 entirely prime magic square, remove the outer layer, it is still a magic square. And it's magic all the way down, my friend. We can remove the next layer. It's still magic. So what are we on now? Like so 13 by 13, and then 11 by 11, 9 by 9, 7 by 7, 5 by 5, and then 3 by 3. It's magic squares all the way in.
One by one.
The
There's
one by
nothing
one,
more.
technically, yeah.
Nothing more magic than the number 5,437 in a square.
Yeah.
I'm scared. That's amazing.
It's so cool. And I want to point out that there is a temptation when we're looking at things like this nowadays to think, oh, human brains could not come up with this. This must have been a collaboration between humans and computers. There would have been a spreadsheet involved, something like that. And I know that in the creation of this one that was not true. And it's the same person that made this one and the previous one that we saw, this one here. Boop, boop, boop. And I found these in a book called Mathematics on Vacation. And the reason I know that no computers were involved is that this was published in like the 50s, which, yes, there were computers in the 50s, but these magic squares were created by someone who at the time was an inmate in prison. They were incarcerated. So they were in prison and they used their time to create these magic squares and then sent them into someone who was gathering together like various different almanac of magic squares. So the human brain really, it's beautiful.
I'm looking
Brings
at
me
this middle bit where the numbers are all in the 3x3 version.
Mm-hmm.
They're like there's some that are about the same size, some that are a bit smaller but about the same size, and then three that are.
The 9,000
Can you check? Can you take your inner square? Is there an algorithm in this paper, or?
No, it doesn't. I've like tried to find out so much information about this person because it
Oh
doesn't
no!
even print their name. It just says that they were an inmate in prison,
Oh,
though they were incarcerated at the time.
oh mean.
Yeah, so
Did Gawar do some work? Not this, but did Gawar do some work in prison at one point as well? Maybe
I
Andrew
don't know.
Vile. I'm gonna look that up. I'm gonna fact check myself and put it in.
Yeah,
Fact check myself and put it in. Put it in further reading.
and that could yeah go into the further. I would love to hear about that into the further reading. Okay, so now we reach another point where we've already used one game to generate magic squares. We did noughts and crosses, and we saw the kind of link between that and magic squares. And I want to put my cards on the table right now and say that I am not good at chess. So, chat, if you know the rules to chess, I guarantee you could beat me at chess. And feel free to. Like, if you ever see me in person, you're like, Ayliean, let's get a chess match in. Yep. You will win. You will win, I guarantee. I don't know where you are in terms of chess, James. Are you a chess person?
Not really. I know how the pieces move, so apparently I'm the favourite in this matchup.
Yeah, so, but you don't have to be good at something to enjoy it. And I love the realm of the chessboard. I love doing things on a chessboard. And there's loads of cool maths that you can do. So, I've made a reduced sized chessboard here. I have what is this? A 5x5 chessboard. And I want to start with something called the Queen's problem, which is how can you place 5 queens on a 5x5 board so that they're not attacking each other. And there's quite a few different ways to do this, so I do have faith in chat. So the queen, just for people that haven't come across it, the queen can attack vertical, horizontal, and diagonal, fully, like as far as the board extends in all of those directions. So let's have a think about it. How could we get 5 queens onto this 5x5 board that are not attacking each other? These are called independence problems.
Okay, and there's coordinates like battleships, so chat could make a plan and then, or they're going to have to make the whole plan.
Yeah.
There's a suggestion straight away to use some sort of knight pattern, because queens can't do the knight thing, which is 2 squares in one direction.
Yep, very well noticed.
Should we just do that? Let's just do that. Yeah. So A1, B3, and I guess C5, and then panic. But I guess maybe...
Realise that you could have gone another way from A1.
I don't want to go to C2 anymore. So maybe I'll go D2, E4. Okay.
Nice.
Maybe?
Yeah.
Just trying to do that like 2 and 1 kind of. Off angled squares. Yeah.
Very well noticed. Because the queen can't do the knight's move, it is a weak point. Queens in knight's move arrangement won't be attacking each other. So a fun thing to think about, because I feel like you got D2 working from B3, but if this worked with Pac-Man rules and went out the other side, it is linked back round to A1. So it's kind of up and then along to, if it was looped around, if it was a torus.
But chess doesn't. Sorry to explain. Chess doesn't have the Pac-Man rule. You can't just go off the other side. I'm always looking for chess matches. Okay, but that's cool that even with the Pac-Man rule, even if you could go off the side and come back in again, they're still not attacking each other. So like that one on B3, even if you let it attack rounds to E5 as well, there's no queen there either. So they're properly avoiding each other, even on the torus. So this is quite nice, and we would call this the N queens problem. But you can do it to any size of board you want. I just thought if you can work on a smaller board, it's a little bit easier, a little bit nicer. We want 5 queens. Okay, so here I'm sure you're not shocked to see a 5x5 magic square, and there is a really nice link between odd sized boards and queen's problems and magic squares. Does it work for evens? Sometimes. I think not all evens. So here's the number 1. This is a normal magic square, if you can remember your definition of normal from the very beginning. What is normal? So it has all of the numbers 1 up to 25 on a 5x5 board. Here is 1, 2, 3, 4, and 5. And I think we can see they are not attacking each other. So the solution to the 5x5 queens problem, this is the mirror image of the one that you found, which is totally fine. Let me do a quick pen color change. So if you put your numbers, your queens on 1, 2, 3, 4, or 5 on this magic square, you have solved the N queens problem for 5x5 board. But then let's have a look at a separate set of 5, 6,
7. I think this is the one that you found. 6, 7. Where's 8? Over here. 8, 9, and 10. And this will continue in successive groups of 5 all the way up to 25. So 11, 12, 13, 14, 15, 16, 17, 18, 19. Like they will give you a solution to the n queens problem. And you can do it both ways. So you can generate magic squares from the solutions of the queen's problem, or you can find queen's problem solutions from the magic squares.
So it's like your patterns in the Jira picture then, because if there's some rule to where they're laid out, then
Mm-hmm.
you can start coming in and saying, oh well, when I look across here or across there, I get, is it sort of one from each category? Oh, that's not quite enough, is it, to be one from each category? But is there some
Like a
logic
lot.
to how they're laid out in there? Not
Um,
really. Oh, sort of.
a little
They
bit, yeah.
The values go up from right to left, 1, 2, 3, 4, and then back round for 5.
So if you allow the Pac-Man rules again, 1, 2, and then knights move background 3, 4, 5. So it's kind of like a ribbon that works its way around.
Mm-hmm.
Hmm.
Does that always happen within these sets of 5? Are they always kind of? I mean, it's right to left, but I can see the blue ones go 6, 7, and 8, 9, 10.
Hmm.
Maybe that keeps happening.
Yeah.
We'll read the
Um,
next ones. 11,
yeah.
12, 13, 14, 15. Right to left.
Like I just think in a world where there's so many times that things just don't work out nicely, and even within the realm of maths, there's so often you think things are going to work one way and then they don't. Magic squares just seems like this beautiful little bubble where it's magic. Like things work out really, really nicely, and luckily, we're in maths. We're always standing on the shoulders of giants. There's so many people that have gone before us that have unearthed these really intricate and fun arrangements of numbers. Um, so I know that we are on time. Um,
Right.
are there any questions from the chat, or would you like to see any more magic squares?
I think they probably would. We have occasionally run over time. I don't want to use too much of your time, but
My time, if I was not here talking to you about magic squares, I would be doing magic squares myself.
right. Well, let's run a bit. Let's run a bit. I'm still interested now. I think I think this is the most revealing thing that you've shown me about how to make a magic square. Like if I find this pattern in where to put the numbers, then maybe I don't have to think about adding at all. I can just just fill it in. Add the blank paper, and if I understand the rules enough, I could just go, oh yeah, 1, 2, 3, 4, 5, and then over there for some reason 6, 7, and 8, 9, and we'll just go sort of march across writing the numbers in
Yeah.
increasing order or something. That's
Mhm.
the most alluring thing to me about magic squares, perhaps, is that maybe I can solve the puzzle, and not
Yeah.
mess around with the equations or anything, or 25 variables. Just go, oh, here we go, off we go.
Some people can do it really, really quickly. Not me, but some people can kind of on the fly, learn to do it and then say, okay, give me a magic number, and then very quickly draw up a magic square that has that number using that kind of technique. It's not
Interesting.
something that I can do.
I
Um,
guess.
so
Oh, yeah.
another chess piece, and I do think this is probably my favorite magic square. So it's a good one to end on, but do not think that this is where the magic square journey ends, because there's so much more, so much that we've not talked about. So this is a knight chess piece, which we've seen is kind of the anti-queen, I suppose. It's the only move that the queen can't do. So for people that have not come across what a knight does, it's a kind of up and along. Some people describe it as an L shape or a 2-1 vector. So it can go up and along, but in any of the directions, along and up, down. So here are the positions that the knight could attack from here, or could move to from here. So
Distance. It moves distance route 5.
cool. So a question that we can ask ourselves is, can a knight visit every single place on a board? So again, useful tactic when you're facing a maths problem. 8 by 8 is large. That's 64 squares to think about. Well, 204 if you count all of the individual squares, but like 64 squares to think about. So reduce the problem, make it smaller. Um, could this knight reach every square on this board? And I know that there'll be a deluge from the chat in a second. They will absolutely get this. What do we think? A 3x3 board. Can you hit all of the squares?
One vote for yes, one vote for no straight away. And the no argument is parity thing. Sorry, somebody wants to do higher dimensions as well. The color. Hang on. When it moves, does it move to a square that's the same color or a square that's a different color?
So knights move to a different color, but they alternate, so they don't always the same color. Yeah. So if it's on a black, it'll move to white. If it's on a white, it'll move to black.
Okay. And this is just a 3x3 board. I missed that bit.
Just the 3x3. Just the 3x3.
Okay. So vote for yes, and somebody saying it can't get to the middle, which I find extremely plausible because I've thought about it doing a couple of moves and then.
That is the perfect counter example on the 3x3 board. So there is no way for it to get to the middle, because if it was to reach the middle, it would have to be on a square which is outside the board. Alternately, if it started on the middle, it couldn't move anywhere. So the middle is a good counter example. So from where we are starting here, its options are to move to here or the other one. And from here, it could go back to where it came from, or it could move up here. And we can kind of start tracing our way around. So it's going from corner to edge to corner. And it can work its way around every other space apart from that central one. Makes quite a nice star shape. I think that's pretty nice looking, but nice counter example. On the 3x3 board, it is absolutely not possible. However, on a 4x4 board, it is also not possible. But
the 4 is even. There's no middle square. So it can't get everywhere on a 4x4.
Yeah, you can. That's further reading. You can convince yourself that it can't do it.
Oh, that's hard. Right, there we go. Okay.
5x5, it can be done. You can work your way around on a 5x5 board. So let's see. There is one that I kind of know off by heart, so I can take us through it. So I would start in the middle for a 5x5. And this is a really nice site because it shows you all of your possible options. So there's the first place that I've picked, and then I can pick any of these options. I am honestly just going to start kind of going round and round and round. So here's where I'm going to go second, and I'm just going to start going round anti-clockwise. Oh, I don't like the auto move. So then I go to the 5th place. Okay, so I'm just kind of going round and round and round and round. And hopefully I can get 25 moves in, and I can hit every single square on the board exactly once. Ooh, my coil's gotten a little bit tighter now, and here I can go to either of these, and I just start hopping in and out of the corner. So yeah, so this is going to work out. This is nice. So there we go. Made it all the way around. That is one of many possible Knights tours on a 5x5. And actually, after 5x5, you can do a tour on any size board. No, don't quote me on that. Actually, I think any size board, but don't quote me.
I did see Onward, and I thought, is that Onward? I've also had that kind of psychic damage effect. I don't know why the magic squares like terrify me so much, but a big square with loads of numbers in has appeared, and I've got a horrible feeling about what you're going to tell me next.
I think you can see what's about to happen. So here's a 6x6. I've done the same thing. I started at 1. This one is particularly nice because it goes back round to where it started. So it finishes on 36, and you can see the 36 and the 1 square, they are 1 away from each other. So this kind of pink line is the route that I took. So I moved that over to the side. And I don't know what kind of music you like, James, but if you've ever been a fan of like metal bands, I think this looks like an unreadable logo for a metal band, like that you just, sometimes they look like you just like can't even see them, or it looks a little bit like a lion, I think. It's a cool pattern. Like it's a very nice, cool design. So that's the Knights tour, but as you have seen, in going around the Knights tour, by giving each move a number, I've created an array. And yes, if I look at the first row, it adds to 111, second row 111, All of the rows add to 111. All of the columns add to 111. Is this a magic? No! Ah, foiled by the diagonals. So this diagonal adds to 92. This diagonal adds to 130. Doesn't have the 111, same as everything else. But hear me out, hear me out. If I were to take 92 and add it to 130, that would get me 222. So like on average,
It feels like it's that feels
yeah,
like one of those algebra facts, right? You're combining the lines or something. Maybe or maybe not. No, maybe that is good. No, I take it back. Maybe that is.
Okay, so
Maybe
there
I
is
do. I do accept that as an additional fact. Sorry. Yes.
there is a name for this. It's a semi-magic Knights Tour. So it's not fully magic, but you are right in your disappointment. We should strive to do better. So it can be done where the diagonals do work. It just needs a bigger board. It can't be done on an 8x8. We're gonna have to go up to, I think this is a 16 by 16. So this is a 16 by 16 Knights Tour, but the exact same thing again. It starts down here, I believe. So like just bottom left, it starts down here. So we would call that 1, 2, 3, 16 by 16. What's that? 256 moves altogether. So it's going to go all the way up to 256. And it finishes up here. So that'll be our 256th one. Here is the magic square. It is a fully magic square, rows, columns, and diagonals from a Knights Tour. Is this? There we go. Have you been satiated with your hunger for an actual Magic Knights Tour?
Yeah, it's also a really nice one, isn't it? Look at that in the middle and the braids around the outside.
Absolutely.
It's just good.
You know what? Nice that you mentioned the braids, because this is created by a technique. Now, obviously, we can't finish there. These two side sections, if you were to take them together, it would also create an 8x8 Knights Tour. Now, remember, it is not possible to have a magic 8x8 Knights Tour, but this is a semi-magic 8x8 Knights Tour. So what you've just described with the braids is actually a technique for creating these magic Knights Tours, which is take disappointing 8x8 semi-magic Knights Tours, split it, and then fill it in the rest with braids. So it's called the split and fix method. So split and then fix it so that you get this beautiful actual magic Knights Tour. And I think this is potentially my favorite Magic Square property, and so I'm happy to finish it there. Also, I don't know if anyone's noticed the big one that's behind me this whole time.
It's only just in frame. Can we get this? Oh, okay. I think if I double click, a bit of a jump. Oh no, I thought that would swap them. It didn't. That's amazing. I love the way. So it's still impressive to me that the braids around the outside fine, but then the complicated bit in the middle is still. I think I have no idea how that's. You made it sound so simple, but also I know that won't be simple at all, right? Looking at the middle bit, and I can't even follow what it does there.
So there's almost these kind of like Lego bricks that build it up. So there are ways of going around corners. There are kind of these little motifs that you can build together that do have a symmetry to them, which help with the magic property.
I see. So if you do one of these going left to right, and then later you come back and go right to left, then.
So as in, like, if you'd started up here, would it still be magic square? Yeah, absolutely. It can work in both directions.
I'm trying to imagine why the braid is. Is it forwards and backwards? Oh, I'm gonna have to follow this line, aren't I? I'm gonna have to follow this line to work out what's going on. Oh no, it's going nowhere near the place I wanted it to go.
If only someone had made a video with a time lapse of drawing this.
Yeah, if only. Just for a reminder, where could I find such a video?
Right. So this is the thing that I'm known for, is doing like time lapses of drawing maths things. So my YouTube channel is just my name, Ayliean. If you want to see that, yeah, it absolutely exists. I will give you a link to put in the further reading that has so much information on Magic Knights Tours. There are multiple PhDs that could be written about this, if people want to go. But it's all just done by people who are doing it for fun. It's yeah.
Nice. I think that's a brilliant place to wrap up. I think unless anyone's got questions in chat, they know that they can put questions. Yeah. So Milky Bar would like one that's like this but gets back to where it started.
Yes. So that's called a closed Knights tour. They do exist, and often they are a little bit less symmetrical, but it can be done. Yep.
I think I prefer the symmetry. I don't mind so much about.
Yeah, I picked this one for its aesthetic because it does look particularly symmetrical.
Very nice, very nice. Good. Okay, I think we'll call it there. Thank you very much, Ayliean, for being on the show again. Thank you to people in chat for joining in with all the polls and questions. My goodness, we had quite a few for you to do this time, didn't we? We'll be back next Thursday, so I'll see you in 166 3/4 hours for another episode of the Oxford Online Maths Club. Until then, have a nice evening, have a nice weekend, and it's goodbye from both of us. Bye.
Thank you.